Hi everyone, my name is Ana Cecy and today I will be presenting Lab 4 on Circuits for Physics 2212. The main purpose of this lab is to use the principles of energy conservation or the loop rule and current conservation, charge conservation, and the definition of steady state to predict the behaviors of circuits containing resistors in series and in parallel. Also, to use multimeters to measure the actual values of conventional current and potential differences in circuits, and to examine the behavior of ohmic resistors and capacitors. After doing these experiments, the values calculated did match my theoretical values and the calculated ones, which I derived from equations in class, considering a very slight margin of error. So here have the fundamental principles used in the slide and their equations, which are loop rule, node rule, Ohm's law, potential difference of a capacitor, capacitance, RC, the definition of steady state, and well, the different components of circuits, which are very important to consider in the lab. Here we were given a specific situation and got asked to predict the currents 1 and 2, which would be measured by two ammeters. And well, first step was to calculate the total resistance, and then to use the equation of m minus the total resistance is equal to 0, considering steady state. And we got that both currents would equal to 0.02 amperes. While doing the same thing in a virtual lab, here we can see that my predictions were correct because the reading of the ammeter says 0.02 amperes when connecting the two batteries and resistors with the respective resistance of 47 ohms and 10 ohms, and the batteries with a voltage, two batteries which each a voltage of 1.5 volts. So here, if we were to connect a voltmeter to the circuit, we would get a reading of 3 volts. And this happens because the black probe gets connected to the batteries. Although it's not in the picture, here the ammeter reads 0 because the circuit is open. So here what I did was to section the closed circuit and measure the potential difference in each section. As you can see here, you can see the measurements. And well, if we were to add them all up, we would get a result of 0 because it is a closed loop. And well, this would satisfy the loop rule. Here we have a graph of potential versus position, and we can see how batteries raise the potential, and wires and ammeters have no effect on the potential, and well, also the resistors, as we would expect, would lower the potential. Of the questions, when you attach the voltmeter to the ammeter, the reading doesn't change because, as we said before, there is a very high resistance for a very small amount of current that's left. And well, when the parallel ammeter circuit is created, currents go through two paths, and the ammeter reads more current of it reads a current of 0.06 amperes. And as you can see, these calculated values are in accordance with the ones of the simulation. We just did the difference in potential over the current, and we got 47 ohms, 100 ohms for each of the resistors, and for the wires and the ammeter we got 0, which was what we expected. Well, now working with RC circuits, when the batteries are connected to the bulb and the capacitor in series, the light bulb becomes very bright and then dims until it comes off as time progresses. And when when the bulb is connected to the capacitor in series, the same thing happens. And well, what's happening to the current is that it starts big in magnitude and then it decreases to 0 as it flows during as time progresses. We were half the times it took for the capacitors to charge with a 10 ohm resistance bulb, we got 9.3 seconds, and then with a 20 ohm resistance bulb, we got 19.4 seconds, and the times for it to discharge were respectively 10.1 seconds and 20.4 seconds. Well, here we have the time-dependent voltage across a discharging capacitor in a graph, and what happens here is that the change in potential at each point, the ln of changing potential at each point over the changing potential at time zero is shown, and we get this graph. Those for time-dependent voltage across the charging capacitor, and well, our present error was 13% considering the expected RC value of 6 seconds minus the actual RC value calculated as shown of 6.79 seconds divided by the expected RC value of 6. This question, in real life, an ammeter would yield readings much slower as the environment wouldn't be perfect. Here we're also assuming that the external resistances plus also the wire and ammeters are negligible. Made the capacitor charge immediately. However, in real life, objects have resistances which slow down the charging process.